Next, we're going to get a more clear understanding of why the chain rule is true. So previously we saw that if we have a composite function, so y is equal to f of u of x, that its derivative, dy dx, is equal to f prime of u of x, and then times u prime of x. So today we're not going to get into a super rigorous proof that is probably best saved for a class on analysis or introductory analysis, but we'll get something that, aside from a few technical details, is pretty close and captures some of the essence of why this rule is actually true. So to do this, since I just have y, I'm going to define a name for this composite function f of u of x. So let me call that h of x. So we'll say that h of x is f of u of x. So basically f is one function. So we have f of u. U is a function, u of x. And this function h is just the composite f of u of x. So h of x is a different function than f, and is a different function than u. For example, f of u could be e to the u, and u of x can be sine of x, and then h of x, which is f of u of x, we take u of x and we plug it in for the u and f of u, so we get e to the sine of x. So it would work something like that. So how do we take the derivative of a composite function like this? Well, every derivative rule always goes back to the limit definition of the derivative. So we know that h prime of x is the limit, as h goes to 0, dangerous territory here. What if I rename this? I'll call this function g instead of h. So we'll say g of x is f of u of x. Just because I only want one like that. So it's the limit as h goes to 0. I don't want to use h here and there, it's confusing otherwise. So we'll change these h of x's to g of x's. So it's the limit as h goes to 0 of g of x plus h minus g of x over h. Right? If you have any function g of x, this is the definition of its derivative. Here g of x just happens to equal f of u of x. Well, the first step, as always, in computing this limit is to take your function, in this case g, and replace it with its definition. So g of x plus h, we take f of u of x and replace the x with x plus h. So we get f of u of x plus h minus f of u of x divided by h. Now the trick here is to do the following. Limit as h goes to 0 of f of u of x plus h minus f of u of x over u of x plus h minus u of x, and then times u of x plus h minus u of x all over h. So I've basically multiplied and divided by a factor of u of x plus h minus u of x. So I've kind of broken this apart into a product of two fractions. So initially I just had this top one up here divided by this h down here, and then I multiplied the whole expression by u of x plus h minus u of x, and then divided by u of x plus h minus u of x. And the whole idea is that the term on the left looks like the derivative of f with respect to u. And then we're multiplying it by a term that looks like the derivative of u with respect to x. That's essentially why it works. Now to get into a little bit more detail, so we'll let u equal u of x. So on the left, we'll suppress the x and just let u be u of x. Now, we'll need to make another assumption that u of x plus h is approximately u of x and then plus some extra factor, so plus w. That's just like f of x plus h is approximately f of x plus maybe, some factor, some change in y. So I'll just say a change in y. Right, so the idea is that if the function u is continuous and h is small enough, u of x plus h will be very close to u of x. So u of x plus h will approximately equal u of x plus a small factor w. And then we have w goes to 0 as h goes to 0. So basically, w is the small correction in the output of u of x. So if I change the input by h, the output will be changed by w. So here w is a function of h, and w goes to 0 as h goes to 0, because as h goes to 0, this just approaches u of x. Right? So given that, we can rewrite the derivative as the limit as h goes to 0 of f of u plus w minus f of u, and then over u plus w minus u. So we have u plus w minus u. And then times, and then on the right I'm going to keep it the same. U of x plus h minus u of x over h. And you could have rewritten this as u plus w minus u as well. And notice that the u subtracts off here. And since w goes to 0 as h goes to 0, assuming that both of these limits exist, so this limit exists, if I take the limit as h goes to 0, and then this limit right here exists, then we can write it as the product of the two. So we have the limit as w goes to 0, f of u plus w minus f of u over w, and then times the limit as h goes to 0 of u of x plus h minus u of x over h. So it's not, I don't think it's 100% tight, but it's there, and it's, it's pretty much has the essence of why the chain rule is true. So what you have on the left is basically the derivative of f with respect to u, right? It's we have the limit as w goes to 0 of f of u plus w minus f of u over w. So that's essentially f prime of u, and then times, and then this is u prime of x. And of course, u is equal to u of x, so it's f prime of u of x times u prime of x. So that's the essence of the proof for the chain rule.